Section. In this section, we introduce Pixtral 12b, a multimodal language model with 12 billion parameters. We designed Pixtral 12b to understand both images and text, achieving top performance on various benchmarks and outperforming larger models. Unlike many open-source models, Pixtral maintains strong text capabilities while excelling in multimodal tasks. We developed a new vision encoder from scratch, enabling the model to process images at their original resolution and aspect ratio. This flexibility allows us to adjust the number of tokens used for image processing. Additionally, Pixtral can handle any number of images within its long context window of 128,000 tokens. Our model significantly outperforms other open models of similar sizes, such as LLaMA 3.211b and Qwen 2VL7b, and even surpasses much larger models like LLaMA 3.290b while being 7 times smaller. We also contribute an open-source benchmark called MMT Bench for evaluating vision language models in real-world scenarios, along with detailed analysis and code for standardized evaluation protocols. Pixtral 12b is available under the Apache 2.0 license. In the introduction, we describe Pixtral 12b as an instruction-tuned model pre-trained on a large dataset of interleaved images and text, enabling it to engage in multi-turn, multi-image conversations. Our novel ROPE2D implementation in the vision encoder allows for processing images at their native resolution, which is beneficial for both low-latency and high-resolution tasks. When comparing Pixtral to similar-sized models, we find that it demonstrates strong multimodal reasoning without compromising text-only performance. For example, it matches or exceeds the performance of models like Qwen 2VL7b and LLaMA 3.211b on multimodal benchmarks, while outperforming many open-source models on text-only tasks. During our evaluations, we noticed that the lack of standardized protocols for multimodal language models can lead to significant performance variations based on minor setup changes. We identified two main issues. 1. Prompts. Many benchmarks use default prompts that are vague, which can lower the performance of leading closed-source models. 2. Evaluation metrics. Official metrics often require exact matches, penalizing answers that are correct but formatted differently. To address these issues, we propose explicit prompts that clearly define the required answer format. We also analyze the benefits of flexible parsing for various models and release our evaluation code and prompts to promote fair evaluation standards. Furthermore, we recognize that current multimodal benchmarks primarily assess short-form or multiple-choice question answering, which does not fully reflect a model's practical utility in multi-turn, long-form settings. To fill this gap, we introduce MMT Bench, a novel multimodal, multi-turn evaluation. Our findings show that performance on MMT Bench correlates well with ELO rankings on the LMSY's Vision Leaderboard. Pixtral excels in multimodal instruction following, outperforming comparable open-source models on the MMT Bench benchmark. Based on human preferences from the LMSY's Vision Leaderboard, Pixtral 12b is currently the highest-ranked Apache 2.0 model, significantly surpassing other open models like LLaMA 3.211b and Qwen 2VL7b, and even ranking above several closed models and larger models like LLaMA 3.290b. Section Summary. In this section, we introduce Pixtral 12b, a 12 billion parameter multimodal language model that excels in understanding both images and text, outperforming larger models while maintaining strong natural language capabilities. We also present the MMT Bench, an open-source benchmark for evaluating vision language models, and discuss the need for standardized evaluation protocols to ensure fair comparisons across multimodal models. Section. Architectural Details. In this section, we describe the architectural details of our model, Pixtral 12b, which is based on the transformer architecture. It features a multimodal decoder for high-level reasoning and a vision encoder for processing images. The model's key parameters are summarized in a table. Our multimodal decoder builds on Mistral Nemo 12b, a powerful language model with 12 billion parameters that excels in various knowledge and reasoning tasks. To enable image processing, we developed a new vision encoder from scratch, called Pixtral VIT. Our aim was to create a straightforward architecture that can handle images of different resolutions and aspect ratios. We designed a vision transformer with 400 million parameters and made 4 significant modifications to standard architectures. 1. Break tokens. We added special tokens between image rows to help the model differentiate images with the same area but different aspect ratios, along with an end token at the end of an image sequence. 2. Gating and feed-forward networks. Instead of using a standard feed-forward layer in the attention block, we implemented gating in the hidden layer. 3. Sequence packing. To process images efficiently in a single batch, we flattened the images along the sequence dimension and concatenated them, using a block diagonal mask to prevent attention leakage between different images. 4. Rotary position encoding, ROPE 2D. We replaced traditional position embeddings with relative rotary position encodings in the self-attention layers. This allows the model to adapt to various image sizes without performance loss, as it focuses on the relative positions of features rather than their absolute locations. Our vision encoder is tailored for multimodal modeling, unlike traditional encoders that are optimized for specific resolutions. This flexibility allows our encoder to handle both high and low resolution images effectively, enhancing performance in multimodal tasks. The complete architecture connects the Pixtral vision encoder to the multimodal decoder through a 2-layer fully connected network, which adjusts the output size of the vision encoder to match the decoder's input requirements. The decoder treats image tokens like text tokens, using causal self-attention to support multi-image conversations. We also introduce MMT Bench, a benchmark for evaluating multimodal instruction following. Unlike existing benchmarks that focus on multiple-choice question answering, MMT Bench assesses the model's utility as a multimodal assistant. It consists of 92 conversations across various image categories, including charts, tables, PDF pages, diagrams, and miscellaneous images. Each conversation is rated by a judge based on correctness and completeness, with results indicating a strong correlation with existing evaluation metrics. MMT Bench is designed to reflect real-world applications of vision language models, focusing on tasks like extraction, summarization, and reasoning. We carefully curated the images, prompts, and answers, ensuring that all prompts require reference to the image for accurate responses. Section Summary. In this section, we describe the architectural details of Pixtral 12B, which integrates a multimodal decoder and a newly trained vision encoder, Pixtral VIT, to effectively process images of varying resolutions and aspect ratios. We also introduce the MMT Bench, a benchmark designed to evaluate the performance of multimodal models through practical conversation scenarios, ensuring that model responses are assessed for correctness and completeness based on image content. Section: Results. In this section, we evaluate Pixtral 12B against both closed and open source models of various sizes, using a consistent evaluation framework. For each dataset, we create prompts that allow us to replicate the results of top multimodal models like GPT-4o and CLAUDE 3.5 Sonnet. These prompts are explicit, clearly defining the expected output format, which helps us accurately assess model performance during testing. All models are evaluated with the same prompts, detailed in the appendix. We also analyze how different prompts and metrics affect model evaluations in the subsequent sections and appendices. Our main results show that Pixtral significantly outperforms all open models of similar size on multimodal benchmarks, as well as closed-source models like Claude 3 Haiku and Gemini 1.5 Flash 8b. Notably, Pixtral excels on MMT Bench, which focuses on real-world applications, and shows strong results on the LMSY's Vision Arena leaderboard, nearing the performance of the largest open-weight models like Qwen 2 VL72b and LLAMA 3.290b. We observe that some open-source models perform much worse than their reported results when using our explicit prompts. For instance, the closest models, Qwen 2VL7B and LLAMA 3.211B, struggle with formatting instructions, leading to incorrect outputs. To provide a fair comparison, we also report their performance using more lenient metrics, which we detail in the appendix. In terms of language performance, we assess Pixtral 12b against similar-sized open-source models on standard text-only benchmarks, ensuring that it maintains strong text understanding while also excelling in multimodal tasks. Regarding prompt selection, we explain our approach to designing evaluation prompts that replicate the reported results of leading closed-source models. We find that many commonly used prompts lack clear output format specifications, which can confuse models. For example, vague instructions for multiple-choice questions can lead to inconsistent answer formats. Our explicit prompts significantly enhance the performance of leading models compared to naive prompts, although some smaller models may perform worse with explicit formats due to differences in their training data. We also discuss the sensitivity of evaluation metrics. Even with explicit prompts, many models still produce outputs in various formats, which can lead to penalties under strict evaluation criteria. To explore this, we evaluate model outputs with increasingly lenient parsing rules. For example, flexible metrics may accept variations like 6.0 for the correct answer, 6. We find that some models show improved performance with these flexible metrics, suggesting that their lower scores stem from difficulties in following prompt instructions. In contrast, Pixtral 12b shows minimal benefit from flexible parsing, demonstrating its strong adherence to instructions and often outperforms other models even under relaxed metrics. Section Summary. In this section, we evaluate Pixtral 12b against various closed and open source models using a consistent evaluation harness and explicitly designed prompts to ensure accurate output formatting. Our results show that Pixtral significantly outperforms comparable models on multimodal benchmarks and maintains strong text performance, demonstrating its effectiveness across both text and vision tasks. Section. Qualitative Examples. In this section, we discuss real-world applications of Pixtral by examining some qualitative examples. We can use Pixtral for tasks like understanding complex figures, following instructions across multiple images, analyzing charts, and converting images into code. For instance, we compare Pixtral 12b with Qwen VL7b and GEMINI 1.5/-8b on a specific example from MMT Bench. This example features a detailed chart about job jitters in the US, which requires precise understanding and analysis. Pixtral provides a complete and accurate response, earning a rating of 8, while Gemini Flash-8b gives incorrect information, and Qwen VL fails to discuss trends adequately.